Well, hello, everybody. Next lesson, right? It seems like we're just cruising along here. This next lesson, following along with our exponential equations, is going to be talking about this idea of growth and decay. Let's dive in a little bit here and we'll see what we're talking about. Let's say that we've got an amount of money, let's say in the bank, or let's say you already have some in your savings account and you're earning money each week, or the bank is giving you money each week. If you find a bank that gives you $10 a week, tell me about it because I want to find that place. But anyway, this is the idea. Let's say that you have $200, okay, and it is growing by $10 each week. Okay, so let's take a look at this one here. If we set up a table, then we can start laying out some information here that'll make it a little bit easier for us to read. So we got our table. We're going to start out with a 0. That's going to be really important. We'll talk about that here in a second. And then 1, 2, 3, 4, 5. You go up to 10 if you want to. Obviously, the more work, but it's up to you. Go up to 3 at least. 4, 5 is probably good. Okay, so we want this 0 value because we want to know what the value is, or we want to have a spot to put the value before it's grown or before it has decayed. That's the important thing. That's why we want to have that 0 value, or what we would call the starting value. Okay. After we have that, or once we've got the table here, we can start putting it in. So our 0 value is going to be the 200, right? That's our starting amount. We have $200 that is going to grow by a certain amount each week. So we're going to put in the 200 in that spot right there. Okay. Then we are going to go and input the next values. It's going to grow $10 each week. So in that first week, the new value is going to be 210. It's going to grow another $10. So it's 220, 230, 240, 250, so on and so forth. Pretty simple there. Okay. This is not an exponential growth. This is what we would call a linear growth because it is only growing by $10 each week, and it's the exact same amount. Remember what we did in our last lesson is that if it is just simply going up by the same amount every interval, then it is just simply linear growth. Okay, so this one's not too bad. This is what we have been used to. Okay, let's look at something that is going to be exponential growth. Let's kind of take the same sort of deal here, but instead of it being $10 each week, we're going to say that it's growing 10% each week, and this is going to give us a little bit of a difference here. So notice that up here, it's 200. We grew it by 10, and it would turn 210. We would add another $10 to it, and it would become 220. So it wasn't really like it was 210. We're adding 10 to it to get 220. It's not like we're adding 10 to the original amount. It's adding $10 to the new amount. So it's going to be that same concept here. So let's see how that looks. First off, start by getting the 0 term in there. Make sure that's your starting value. And then let's start inputting here. First value, obviously 200. Basic. So the next one is going to be by adding 10% to it. So what is 10% of 200? Well, it would be $220, or $20 is what's being added. So your next value is going to be 220. So then now we need to find 10% again, but it's not 10% of the starting value. It is 10% of this value, because remember, we were adding $10 to this value, and then $10 to this one, and then $10 to this one. So down here, we need to find 10% of this. Well, that's not going to be 20 anymore. That's going to be $22. So we would add that. We would get $242, and then we would want to find 10% of this amount, which is going to be $24.20. So we would add that. And then 10% of this amount, $26.62. And then 10% of that amount. Okay, so you see how that works. Okay, here's just some things over here that we can take a look at and see the comparison here. 10% of 200, you would just multiply it by 0.1. Okay, if you guys are thinking about your calculator, that's just what we're doing here. So then you would add it there. Or another way to do this is, so this is how to figure out what your percentage is, or how to figure out what your new value is. You find 10% of it, and then you would add it to it. But there's another way to do it. If I wanted to figure out what 20% or 10% of 200 is, and then add it to it automatically, then I could multiply it by 1.1, because that would be multiplying the 200 by a whole 1, which would give me 200, and also a 0.1, which is going to be 20. So that allows me to get my next value right away. So here's a little trick. So if I wanted to go by 15%, and I wanted to add that to it, then it would be multiplying it by 1.15. Okay? So little trick over there. Rewind it to review that if you need to. So remember our exponential function. This is from our last week here. Y equals a times b to the x. Okay, a was our y-intercept essentially, and then B was our constant ratio. Okay, remember those terms. Go back and view that video if you need to, because we're going to be modifying that a little bit for this one here. Okay, f of x equals a times b to the x. Remember, the f of x is essentially interchangeable with a y, but this really gets us into our function notation. So you're going to want to make sure that you use that there. So a is the y-intercept, b is the constant ratio. Again, so in here, what we would look at if we wanted to interpret it for this one is f of x, our starting value is going to be 200, okay? And then our constant ratio is going to be this 1.1, okay? This value down here. So it's the same concept, it's just the way that we can actually multiply it. Instead of trying to say multiply it by 0.1 and then adding that to the original amount, we can just put the 1.1 here. Okay, so our constant ratio is 1.1. What you could put up here is you could say 200 times 1.1, 220 times 1.1, 242 times 1.1. Okay, and again, see the previous lesson because that's where we talked about how that constant ratio works here. Okay, so if we wanted to put in, let's say, how much money we would have after 52 weeks. Okay, let's say we put that $200 in there and it's growing 10% each week. By the way, again, you find this bank, let me know because I'm going to put all my money in there. After 52 weeks, so we would put f of 52. Okay, so this is our input. Okay, so in our equation, the x, notice the x is here, this is our input, we would replace it up here. So 52, we're going to replace the x in the equation up here with 52. So, sorry, that went a little bit too far for you. So it's going to look like that, okay? So we're going to have 200 times 1.1 to the 52nd power. 52nd power, okay. It's pretty crazy. You do that in your calculator. Here's what you're going to have. You're going to turn $200 into $28,408.59. Pretty crazy. Obviously, you're not going to find a bank that does that. I don't know, maybe grandma, if she's feeling really generous, but most likely you're not going to find a bank that's going to do that for you. But anyway, that is how that works. Okay, so let's keep going here. Let's get another one. Sorry, I always go too fast there. Okay, what if it was 2%? Okay, so this is what if instead maybe a little bit more realistic and still, 2% each week is still pretty crazy. But if it was 2%, then our equation would only change right up in here. Okay, the constant ratio. So instead of it growing at 10%, which is the 0.1, it's growing at 2%, which is 0.02. Okay, so you guys could solve this out. Again, you put 1.02 to the 52nd power in your calculator, multiply it by 200, you would find your answer there. Okay, I'm not going to worry about putting it there. But the growth model, okay, here's what we're looking at, the growth model. A of t, t meaning the term, okay, and we'll talk about that in a second here. A is the starting value, and this is sub-zero. Okay, this is not like to the power of 0. Remember, the powers would be up here. So this is a sub-0, and this 0 is corresponding to this 0. Remember, our starting value or our zero term. Sorry, my speech wasn't working there. So the starting value there. And then what we've got here is this part right here, and this is where this makes sense. So we've got 1 plus our rate. Okay, so imagine that we look back up here, we've got 10% was our rate. Well, it's 1 plus the 10%. Well, 10% is 0.1, so that's where we get this 1.1. So this is how this works out. We take whatever our rate is, and we would add it to 1, and that would give us our growth model. Okay, and then we have to the term, the power of the term. Okay, so it's very similar to our exponential function equation that we had over here. Exponential function equation, redundant. Very, very similar. Okay, if you can look at it, it's got some different variables in there. Okay, it's a starting value here, and then the percentage rate is what we're looking at here. Okay, all right. The decay model is going to be slightly different. What if this is decreasing? So let's say it's money that's coming out of your bank account every month as opposed to going into it. Okay, then what you could do is instead of it being 1 plus the percentage, hopefully you're thinking of this, it'll be 1 minus the percentage. Okay, so let's say it was decreasing by 10%, 1 minus 10%, or 1 minus 0.1 would be 0.9. So your growth, or your rate, your constant ratio, would be 0.9. Okay? All right, so let's do a couple examples here. In 2000, the U.S. population was 280 million. there was a 0.85% or 0.85% growth rate. Find the population in 2018. Now, this is 0.85%. This is not 85%. That would be pretty crazy. So 0.85% growth rate. So let's start filling out our equation here. So A of t equals, and what would our starting value be? Remember, that's going to be our first value there. It's going to be the starting value, a to the 0. So think about what that would be. We're going to multiply it by, and this is a growth rate. Notice it's growth, so we're going to put 1 plus r, and that'll be to the power of t. Okay, so let's start filling that in. What would be our starting value? Okay, well, it says in 2000 the population was 280 million, so we're going to say 280 million. So our starting value is 280. Now, notice I'm not going to put the bunch of zeros here. We're going to solve this in terms of million, okay, because it'll still work out. So we can, when we get our answer, we'll just have to remember that. So 280, and then what would be our growth rate? So what would be this term inside here? So it's growing at 0.85%. How would we write 0.85% as a decimal? Don't say 0.85 because it's a decimal already, so we would have to move that over, the decimal place over twice, so it's going to be 1.0085. Okay, that is going to be our growth rate. Okay, 1 plus 0.85%. Well, 0.85% is 0.0085. And then we need to the power of, and this is where our term comes from, so how many years is that going to be? Well, it started in 2000, it's 18, so it would be to the power of 18. So really this should be a of 18 right there, okay? So if we plug this in, we would get this one right here. So you can pause and see what that, you can plug that into your calculator, 1.0085 into your calculator to the 18th power, and you would get, after you multiply it by 280, 326.08 million people. Okay, so this is how that works. Again, rewind it, go back, make sure you've got this example written down here because you're going to be using these a lot. Okay, let's do another one. This one we're going to talk about possibly something other than growth. Maybe, yeah, this one's decay. So the value of a car drops 12% each year. That's our indicator that it's a decay. Okay, if it said it grew, then it would be a growth rate. If it's dropping or going down, it's a decay. What will the value of a $29,000 car be in 10 years? Okay, so let's start filling out our equation here. So A of t equals our starting value, which is a to the 0, 1 minus r to the power of t. Again, this is the decay equation. Don't forget that it's minus there, okay? So then what would our starting value be? $29,000. Okay. And notice that right here we did put in a of 10, meaning that it's going to be after 10 years. Okay, so this is the mistake that I made up here. I didn't put 18. I should have had that right here. This one is where you put that number. So a of 10 is going to equal 29,000 as our starting value. And then our decay rate is 1 minus our rate. Well, what is 12% as a decimal? 0.12. So what is 1 minus 0.12? There we go, right there, okay? 29,000 times 0.88 to the 10th power, okay? Solve this, put this into your calculator, multiply it by 29,000, and you get about $8,076.53, okay? Sad reality is that that's pretty much true. You can buy a $29,000 car, and in 10 years from now, it's going to be worth way less than half of it, but that's just the way it goes. Hopefully you got a good 10 years out of it. Okay, so that is how our growth rate works, and that is how our decay rate works. Okay, so a couple examples for you here. Okay, there's another thing we haven't talked about yet. It's along the same lines, but it's compound interest, and this is where it starts getting crazy. Okay, take a break, go to the bathroom, get yourself some water, relax, and then come back and press play, because compound interest is going to take it up a little bit here. So compound interest. This one is what you're more likely going to find when you're dealing with things like credit cards or stuff like that. So this is where we're going to be looking here. It's in a way it's going to be similar. You're going to see some similarities, and then you're going to get kind of blown away when we get to a little part of it here. So A of t equals P, and P is going to be the principal amount. Principal meaning the initial amount. Okay, could be the starting value of a loan, could be the starting value of a debt, whatever it may be. Okay. And then, oh gosh, look at that. It's painful to watch. Okay, 1 plus r over n to the power of n times t. What is going on here? Okay, let's identify some things in here. Okay, this one up here, the r, is the same thing like it was before. It stands for the rate, the percentage. Okay, the n, and this n here and this n over here, again, it's in this one equation, so they have to be the same thing. This n stands for the number of compoundings each year. So we'll talk about what a compounding interest rate is in a second, but this number right here, this n here, is talking about the number of times it compounds in a year. And the t really stands for the year, okay, the term, essentially the same sort of deal like we had before. Okay, so compounding means we could say something like you've got a $2,000 loan and the interest on it compounds quarterly. Okay, how many quarters are there in a year? Obviously there's 4, so that n value would be 4. Okay, and then the t would be however many times or however many years you're going to have the loan or something like that. Okay, so let's look at an example. This one here, $2,000, we're going to start as our principal amount, and it's 2.5% quarterly, so that's where the compoundings comes from, and then it says for 5 years. Okay, so let's try and plug in our information here. Looking at our equation, a of t, well, what is t going to be, do you think? That's going to be 5. Okay, so there's our number of compoundings, and then or not number of compounding, sorry, that's the number of years. That's our term length, the length of the loan. And then we need our principal amount. Okay, that's the very next thing. Well, that should be 2,000. Okay, and that's where we're going to start. Okay, and then the next thing is we have this funky stuff right here. So it's 1 plus, so we're going to put a 1 plus, and then we need to figure out what is the rate. Well, the rate is 0.25%. So how do we write that as a decimal? 0.025 on top there, 0.025, okay? And then the n, remember that's the number of times it compounds in a year. How many times is it going to compound in a year if it is quarterly? Quarter, there's 4, so it's 4 times, and then up top here it's going to be 5 times 4, okay? Or 4 times 5 if we wanted to follow this. Okay, so that's how that looks. Ugh, gosh, it looks icky, but it's really not that bad. We can do 5 times 4. That's simple. We can even do this in here. This isn't too bad. So let's get that done. 2,000 is going to stay on the outside. Let's simplify what's in here. 1 plus 0.025 divided by 4. Bippity boppity boop. We get 0.10065. Use your calculator, folks. Calculator is a tool. It's not going to solve the entire question for you, but it helps you along the way when you got to do stuff like this. There's nothing wrong with that. Okay, and then up here it's 5 times 4, so that's to the 20th power. Okay, now we need to get back to exactly where we were. If you guys look at this, and when I jump back over to the, if I were to, I'm not going to, but if we jump back a little bit, this looks exactly like the previous functions that we've had. We're going to take this, raise it to the 20th power, multiply it by that, and we get our answer. $2,265.42. So that means that this particular loan would have grown by $265.42. So if you were to borrow this $2,000, by the time you have to pay it back, you would have paid back $2,265.42. That's the idea here. Okay, it's a little bit more basic than what you'd find in a, like an education loan or something, but you'll get the idea. So this is how a compound interest equation works. I'm going to leave you with this example, which means that you're going to use the worksheet to really try it out. If you have any questions, come back and look at the video, send me an email, hop on the video chat. Be happy to work through these with you. In fact, my video chats, sometimes I can get really lonely, so come and say hi at least, if nothing else. And I'm weird, and I'll like to solve the math with you guys. So anyway, give it a shot. Let me know if you have any questions. And most of all, have a great time. See you later.